So in today's lesson, we're going to talk about moles, mass, and molecules. We've already gone through the mass to the molecules or particles phase, so we're going to review that really quickly, and then we're going to see how we can transition to mass to moles, and then how we can go from mass to molecules. So we can figure out how many particles are in a specific amount of a specific amount of a compound or an element. This is very important for us when we start looking at doing chemical reactions. We're looking to see how much we have to use, especially when we start talking about molarity and the strength of certain solutions. So it all kind of ties in. I know it's hard to see right now, but it is very important. And it's going to keep building. So this is very important for our future work with things like stoichiometry and chemical reactions, which will come in future units. So moles. So previously we talked about moles. Okay, they're not the little critters that are in the ground. These are the amount of a substance. Okay, and it's the number of particles in a formula unit. In a formula unit the amount of particles, molecules, atoms, formula units in a substance. So we talked about Avogadro's number. Okay, that's our conversion factor. Okay, remember Avogadro is to avocado, like mole is to guacamole. Okay, you need avocados to make guacamole. You need Avogadro to do a mole. So that's our number of 6.022 times 10 to the 23rd. Particles, molecules, atoms, formula units, chicken sandwiches, whatever that amount thing is. Okay, so let's take a look with our practice problem just to kind of take a step back. Remember, we're going to use our T-chart or our railroad tracks. It's a dimensional analysis conversion. Okay, our conversion factor is that 1 mole equals 6.022 times 10 to the 23rd. So I make my T-chart. I put my given in the upper left corner. So the given in my problem is 7.65 moles of argon. Okay, and you can see I labeled it. Labels are important. Labels are going to help us as we see that this chart is going to get longer in our questions. Okay, to get rid of moles, I'm going to put it on the bottom. And I know that 1 mole equals 6.022 times 10 to the 23rd because here's my conversion factor right here. Okay, so I would cross out my moles, and I get 4.61 times 10 to the 24th particles. Okay, I'm going to multiply across because they're next to each other, and I'm going to divide by the bottom, which is just 1. Okay, so hopefully you remember doing that in the past. Okay, so now we're going to take it a step further. So let's talk about molar mass. Molar mass, okay, is the weight of the atoms in an element or compound. Every element and compound has its own molar mass. Okay, it'll always be the same thing. Okay, to figure out your molar mass, we're going to use the average atomic mass, okay, or the atomic mass, which is found on the periodic table, okay, to calculate your molar mass. So your average atomic mass is that number on the bottom. It's normally one with a It's normally the one with a decimal point in it. Okay, so your atomic number normally is going to be on the top. It's going to be a whole number because remember your atomic number is telling you the number of protons, okay, and the number of electrons in a neutral atom. Your atomic mass is the one that's normally going to be on the bottom. Not necessarily, but most periodic tables it's on the bottom, and it's usually going to be a decimal. Okay, so we're going to use that to calculate. So first we're going to do an element. We're just going to look at magnesium. So if you look at magnesium, it's Mg on your periodic table. And if you look, it says 24.3050 if you're using the periodic table on the wall. If you're using the one in your little blue Bible, it probably will just have 2 decimal places. But for our purposes, when we are calculating molar mass, we're going to use to the 1 place after the decimal point, to the 10th place. So you're going to use the whole number in the front, decimal point, and then one number after the decimal point. So for us, it's 24.3050. So I'm going to go, again, you're going to do that 24.3050. We're going to look next door to the 3 because that 3 is in that first decimal place. Next door is a 0. That 0 is going to keep my 3 the same. So my answer is 24.3. Then because I only have one atom of it, I don't have a subscript after the G, and I don't have a big number or a coefficient in front of the M. I'm just going to do times 1. Okay, and so my molar mass is 24.3 grams per mole. Okay, let's try another one. Okay. In this one, our oxygen is called a diatomic element. Diatomic means you have to have 2. You cannot be left alone. Think of diatomic elements as elements that are like four-year-olds. You can't leave a 4-year-old alone. So they're always going to be paired with either another element or they'll be paired with themselves. And they're going to have a subscript, which is this little number right here, okay, next to them. Okay? Think of subscript, the subway, you're going to go underneath, okay, on the bottom. And then there's also things called superscripts, which we're going to look at a little bit later. And superscripts are like Superman. And Superman flies above, they are up over the world. Okay, so I'm going to look here. I have oxygen. So I'm going to look up oxygen on my periodic table. And it has an atomic mass of 15.9994. Okay, so if I were to go one decimal place, it's 15 is the whole number, 0.9, next door to the 9 is another 9, so that's going to bump that 9 to a 10, so technically that 15 is going to bump up to a 16, right, because you can't have a tenth or 10 tenths, that becomes a 1. So 16 is our mass, and because oxygen is O2, I'm going to have to multiply this by 2, so my answer is 32 grams per mole. So the the molar mass of O2 is 32.0 grams per mole. Okay. Our final one we're going to look at is water. Okay, or H2O. Okay, this one is a compound. The other two were elements. This one's a compound because I have 2 or more elements together. So what I'm going to do is I'm going to find the mass of each of the elements, including the number of atoms there are. So if there's any subscripts, I'm going to use those. Okay, and then I'm going to add those together. So hydrogen is 1.00794. So again, looking at that first decimal place, it's a 0. Next door is another 0. So it's just 1. And because I have a subscript of 2, I'm going to multiply by 2. So the mass of the hydrogen is 2 grams per mole. Okay. I'm going to do the same thing with the oxygen. We figure oxygen was 16 from our last one. Okay, in this case, I only have one atom because there's no subscript. Okay, and so it's 16. So I'm going to take those two numbers. I'm going to add them together. And I get an answer of 18.0 grams per mole. So to convert from mass to moles or moles to mass, we're going to use our molar mass as our conversion factor. So 1 mole is the molar mass of your element or compound in grams. So we're going to do one example together. So how many moles are in 100 grams of sodium? So first, I'm going to figure out my molar mass of sodium because I need to figure out my conversion factor. So sodium is Na. If I look on the periodic table, sodium is 22.989707. I'm going to look at my first place after my decimal point. It's the 9. Next door, that 9 is an 8, so that's going to get bumped up. Okay, again, I cannot have 10 tenths, so I'm going to bump it to 1, and so 22 becomes 23. Okay, I only have one of them. Okay, Na doesn't have a subscript, so 23.0 times 1 is 23 grams per mole. Next, I'm going to make my T-chart. okay, because I'm going to do my conversion factor, and I'm going to look at what's given to me in the problem, and it says that I have 100 grams, okay? So I'm going to put that in my upper left. To get rid of grams, I'm going to use my conversion factor, okay? And I'm going to see that grams is going to go on the bottom. Now, the number goes with grams. So 23.0 will go with the grams label. Okay, so we'll put that there. And then also, it's per mole, which means it needs 1 mole. So mole is going to go on top, gram is going to go on the bottom. I'm going to cross out my labels that match, so grams, NA, and I'm going to divide 100 by 23, because 100 times 1, because those are next door, divided by a bottom, and I get an answer of 4.35 moles. Now, you probably get a longer answer when you put it in the calculator. However, I want to use significant figures, and my significant figures are 3 because I have this decimal point. My zeros actually count. So my answer is 4.35 moles. Okay? Let's try another one. How many grams in 2.5 moles of CO2? In this case, I have a compound, so my molar mass is going to take a little extra step. It's not just going to be something I can read off of the periodic table. It's going to take a little bit more. So, carbon dioxide, that's CO2. My C, if I look on the board, is 12.011. So first decimal place is 0. Second is the 1. So I'm going to just put 0. Okay, and I have one of them according to my formula, which is CO2. Okay, I'm going to do the same thing with oxygen. Again, we've done oxygen previously, okay, but it's 15.9994. So first decimal place is the 9, next door is the 9. I'm going to have to round up. I can't have 10 tenths, so that becomes 1, so it becomes 16. Okay, I have 2 of them because it's O2, so 16 times 2 equals 32. Those two numbers, 12 and 32, I'm going to add together, and so the entire mass of CO2 is 44.0 grams per mole. So next, I'm going to go ahead and draw my T-chart, okay, and in my T-chart, I'm going to put my given, which is 2.5 moles, so that's going to go in my upper left, okay, and then to get rid of moles, I'm going to put the number mole, or the letter mole, the word mole, in the bottom right corner because I want them to be diagonal so I can cross them out, and I know from my molar mass that I just solved that 1 mole equals 44 grams. So that's going to go on top. Okay, and once I cross out moles, I'm just going to multiply across 2.5 times 44 and divide by 1. And my answer is 110 grams of CO2. Okay, and again, I want in 2 significant figures because 2 significant figures is what my original given was in, okay, with the 2.5.